Multiple regression. This is general multiple regression. None of the fancy stuff. No mediators and moderators. Not yet. They're coming. But in a nutshell, multiple regression, you try to come up with other variables, IVs, predictors, that can significantly predict what the DV will be for any given subject. Okay? So by the DV, we're talking about the variance. You assume that all the variance in the DV is right here in this circle. And then you get some IVs, different IVs that are measuring different values. So let's go over some terminology. An IV in a multiple regression model is called a predictor. So these are the predictors, and the DV is the output or the criterion. Now remember, all multiple regression models are prediction models. You're trying to take information from the IVs and predict what the DV is going to be. That's what this whole thing is about. But now I'm going to drop the variance, right? We're talking about the variances matching up here. But what we normally do is we take a correlation between an IV and a DV. And if you got more than one IV, you take a different correlation, right? So you get three different correlations. Some will be strong, some will not be strong. Some will be significant, some will not be significant. Another way to look at it is to see what kind of variance that one IV kind of overlaps with the other DV, with the DV. That's another way to look at correlation. Okay, this is what we call shared variance between the IVs and the DVs. And it's basically the same thing as a correlation. So if an IV is strongly correlated with a DV, it will share a lot of the variance with that DV. You see that? So there's another way to think about the correlation, the shared variance between the variables, whether it's a strong predictor or not, that kind of thing. So let's pretend you're working in the human resources department of some giant company, and you're trying to predict what makes job promotions. In other words, do the number of sick days predict how many promotions a person will get, how long the person's been working for the company, or how satisfied they are with their job, right? These are the predictors, and this is the criterion or the DV. So, analyze, regression, linear. So the DV is job promotions. Let me move this so you can see it. Job promotions. IVs are sick days, years in the company, and job satisfaction. And we want to click all those boxes. We want the Durbin-Watson. Plots. Z-pred on the X, Z residual on the Y. Remember, this is going to check for homoscedasticity after we stick the lowest line in. And the only thing we want here is the Mahalanobis. That will tell us if we have multivariate outliers. Click OK. All right, here's our output. Really don't care about the descriptives, mean, standard deviations, not in a regression model anyway. Correlations, we can use this to check the assumption of linearity. Again, if any of these correlations between the IV and the DV is really close to zero, that means that it might have violated that assumption. And I don't see any of these close to zero, so I'm assuming it did not violate the assumption of linearity. This box tells us if it was a standard or a regular multiple regression, hierarchical or stepwise, and this was just a regular one. First box you're going to look at is your ANOVA. This means that it was a significant regression, so proceed. So if the ANOVA is significant, the model is significant. Second thing you look at is the R-square. That's a huge R-square, but again, I just make up this data as we go along. And what that means is that 70% of the variance in the job promotion can be explained by your IVs, by this model, which is really, really good. Adjusted R-squared. What that means is if you did this exact same study with a different sample, then your R-squared would drop down a little bit. Or another way to interpret this is the adjusted R-squared might be applicable to the population. Got it? And these numbers should be relatively the same. This one will always be a little bit lower. If there's a huge difference between the R-squared and adjusted R-squared, You got some issues somewhere. All right, moving right along. Since we're up on the model summary box, the Durbin-Watson tells us if the assumption of autocorrelation has been violated. And it's supposed to be between 1.5 and 2.5, and it's right in there, so I'm assuming that it did not violate the assumption of autocorrelation. So let us continue. Here's your coefficients box. And this will tell you which of your predictors are significant. So let's look at sick days. You go to the beta weight, negative 0.661. So in other words, the less sick days taken, the more promotions, and it is significant. Right? Years of service. So that means the longer you've been in, the more promotions you're going to get, and that too is significant. Job satisfaction, it is not significant. Okay? So job satisfaction really doesn't have anything to do with the number of promotions you're going to get. Collinearity, we're not going to worry about that. But with multicollinearity, let's check that assumption. It's over here, right? The tolerance and the VIF. So if any of these tolerance numbers are less than 0.1, it violated that assumption. VIF, if any of these numbers are greater than 10, it violated that assumption. And I'm not seeing any violations anywhere. Moving down. So our Mahalanobis distance, this number is the biggest one we have from our data set. And you should probably just memorize it. If you got 3 predictor variables, your maximum Mahalanobis distance is going to be somewhere around 17, 18, something like that. So you did not violate the multivariate normality. We're going to check the homoscedasticity. You're going to double click, pull up the editor. You're going to add the best fit line and the lowest line. Click OK. And this looks like it did violate the assumption of homoscedasticity. This line should be relatively smooth and flat, like a horizontal line. So again, it looks like it did violate the assumption. Get out of there, you. And the last thing I think I'm going to test you on is you got to know how to write up the prediction equation. So with the prediction equation, you use these values right here, unstandardized coefficients, just the B weights. So it's going to be predicted Y equals, you start with the constant number, it's going to be 4.305, and then you drop down to only those significant predictors. So it's going to be Y hat equals 0.4305 minus 0.730 times the number of sick days taken plus 0.047 times the number of years in service. Do not use job satisfaction because it was not significant. And then you just put plus a little bit of error. But that would be the prediction equation or the regression equation. So that's everything I'm going to test you on. I want you guys to practice these things. Practice, practice, practice. All right. MGZ.